Right now, as you sit there, something is going through you, not around you, through your skin, through your bones, through your skull, through every organ you have. It went in one side and it came out the other, and it did not stop, it did not slow down, and it did not ask permission. And it is not one thing, it is 100 trillion of them, every single second. You did not feel it. You will never feel it. And for 26 years, the smartest people on the planet could not even prove these things existed. So how do you catch something that refuses to be caught? See, I love this kind of problem because it starts with a crime. Something was stolen, and the detective work that went into figuring out what was stolen and who the thief was and how the thief got away with it, well, that story is one of the most beautiful in all of physics. It took half a century. It required going a mile underground into an old gold mine. It demanded a tank the size of a swimming pool filled with dry cleaning fluid. And even after all that, the answer turned out to be stranger than anyone had guessed. But let me start with the crime scene. The year is 1914. Actually, no. Back up a bit further. The year is 1900, right around there. And physicists are staring at a thing called beta decay. This is one of the ways a radioactive nucleus falls apart. It spits out an electron. Simple enough. You have a nucleus sitting there, it is unstable, and it coughs up an electron and turns into a slightly different element. Fine. The thing about this is if you have two objects and one of them breaks into two pieces, you can do the accounting. You know how much energy the original had. You know how much the leftover piece has. So the electron that flew out should carry a very specific amount of energy. One number. Every time, like a vending machine, you put in your coin and you get back exact change. But that is not what happens. Physicists measured the energy of those electrons, thousands and thousands of them, and what they found was a mess. The electrons came out with all sorts of different energies. Some had a lot, some had very little. There was a whole smear of values, a continuous spectrum they called it, and no two electrons seemed to agree on how much energy they were supposed to carry. That is the crime. Energy was missing. Not a little bit of energy. Sometimes most of the energy. The nucleus decayed, the electron flew out, and the books did not balance. Energy went in, less energy came out, and nobody could find the difference. Let me put it another way. Imagine you have a cannon. You load the same charge every time, same powder, same ball, same everything. You fire it. Sometimes the cannonball comes screaming out at full speed. Sometimes it limps out like a lazy throw. Sometimes it barely dribbles from the barrel. Same cannon, same charge. Wildly different results. That would drive you mad. You would tear the cannon apart looking for the leak. And that is exactly what the physicists did. They tore apart their experiments, checked their instruments, redid their measurements, and the answer kept coming back the same. The electrons had a continuous spread of energies, and nothing visible could account for it. It was not just the energy either. Momentum was coming up short. Angular momentum, the spin of the particles, was off. The nucleus before the decay had one spin. The nucleus and electron after the decay had a different total spin. Something was carrying away angular momentum too. The whole transaction was crooked. Multiple quantities were being siphoned off by an invisible pickpocket. Now this might sound like a bookkeeping error, but energy conservation is not some suggestion. It is one of the deepest laws in all of physics. You do not just shrug and say, well, I guess some energy wandered off somewhere. If energy is not conserved, then the entire machinery of physics, everything we have built since Newton, starts to wobble. And some very serious people did consider that possibility. Niels Bohr, one of the giants, he was willing to throw out conservation of energy at the atomic scale. He said maybe energy just is not conserved in these small processes. Maybe it is only conserved on average, statistically, in the big picture. He was not joking. He wrote papers about it. He was ready to burn down one of the pillars of physics to explain this spectrum. But there was another man who was not ready to burn anything down. His name was Wolfgang Pauli. And Pauli was a very particular kind of physicist. He was brilliant, and he was nasty, and he was almost always right. He once dismissed a colleague's paper by saying, "It is not even wrong," which in Pauli's mouth was worse than any insult. He had a reputation for being so critical that experimental equipment supposedly malfunctioned when he entered a laboratory. They called it the Pauli effect. And in December of 1930, this man, this relentlessly exacting man, did something desperate. He wrote a letter. The letter was addressed to a group of physicists at a conference in Tübingen. He did not attend the conference himself. He said he could not come because he had to go to a dance in Zurich. Whether that was true or not, I cannot say. But the letter was historic. He started it by addressing the recipients as dear radioactive ladies and gentlemen. That was Pauli for you. Even in his most daring moment, he could not resist being Pauli. He wrote, and I am paraphrasing here, that he had hit upon a desperate remedy to save the law of conservation of energy. He proposed that inside the nucleus there existed a new particle that nobody had ever seen, a particle with no electric charge, a particle so light it might have no mass at all, a particle that was emitted alongside the electron during beta decay, carrying away the missing energy. He called it the neutron, actually. This was before Chadwick discovered the real neutron in 1932. After Chadwick found the heavy neutral particle in the nucleus, Enrico Fermi renamed Pauli's little ghost. He called it the neutrino, the little neutral one. Pauli himself was embarrassed by his own idea. He said something to the effect of, "I have done a terrible thing. I have postulated a particle that cannot be detected." He called it a sin, and he meant it half seriously, because that was the rub. This particle, if it existed, had no charge, had little or no mass, and interacted with matter so feebly that it might as well be invisible. How on earth could anyone find such a thing? Let me give you a sense of just how invisible we are talking about. Take a single neutrino, send it toward a wall of solid lead, not a thin wall, a wall of lead 1 light-year thick. You know how far a light-year is? That is about 6 trillion miles, almost 10 trillion kilometers. Picture a slab of lead that stretches from here to the nearest star. A neutrino could pass through that entire slab and come out the other side without touching a single atom. The odds of it interacting are roughly 50-50. For 1 light-year of solid lead, that is not a particle that wants to be found. That is a particle that has made a career out of not being found. And for 26 years after Pauli's letter, nobody could find it. People started calling it the poltergeist, a ghost, an accounting trick. Some thought maybe it did not exist at all, that Pauli had just invented a bookkeeping fiction to save a law he loved. But then 2 men decided to try anyway. Their names were Cowan-Reines and Clyde Cowan. They were working at Los Alamos, which, is where they built the bomb. And Reines had been thinking about this problem. He asked himself, what would it take to actually see a neutrino? Not infer it, not deduce it, see it, catch it in the act of doing something. He went to Enrico Fermi, who by this time had built the whole mathematical theory of beta decay around the neutrino, and he asked Fermi, how would you go about detecting one of these things? And Fermi thought about it and said, I do not know how you would make such a detector. Coming from Fermi, that was devastating. But Reines did not give up. The story goes like this. He ran into Clyde Cowan at Los Alamos, and they were both heading to Princeton for a meeting about fusion research, and their airplane got grounded in Kansas City because of engine trouble. So there they sat, stuck in an airport with nothing to do. Reines started talking about the neutrino problem. By the time they left Kansas City, they had the outline of a plan. The neutrino detection experiment was born from a flight delay. Physics history sometimes turns on moments like that. The original idea was insane. They wanted to use a nuclear bomb as their neutrino source. An actual weapons test. They would lower a detector into a hole in the ground roughly 40 meters from the tower where the device would be detonated. The neutrino burst from the fireball would last only a fraction of a second, but the flux would be absolutely monstrous. They figured they could catch the signal before the shockwave obliterated everything. I am not making this up. They got approval for it. They called the project Poltergeist because they were hunting a ghost. Fortunately, a senior physicist at Los Alamos named Kellogg suggested they try a nuclear reactor instead. A reactor is a tremendous steady source of neutrinos. Every fission reaction in the fuel rods triggers dozens of beta decays, and each one, if Pauli was right, produces a neutrino. The flux streaming off a big reactor is on the order of 10 to the 12th or 10 to the 13th neutrinos per second through every square centimeter. You could sit there for months collecting data, and your equipment would survive the experience. Much better than a bomb. So here is their idea. If a neutrino can be produced in beta decay, maybe it can do the reverse process. An antineutrino comes along. It hits a proton, and it produces a neutron and a positron. That positron is the antimatter partner of the electron. It immediately runs into an electron, they annihilate each other, and you get two gamma rays flying off in opposite directions. Then a few millionths of a second later, the neutron gets swallowed up by a nearby nucleus, and that produces another gamma ray. So the signature is this: flash, flash, then a tiny delay, then flash again, two gamma rays at the same instant, followed by a third gamma ray a few microseconds later. If you see that pattern, and you see it repeatedly, and the rate changes when you turn the reactor on and off, then something from that reactor must be hitting the protons in your detector. Something with no charge, something you cannot see any other way. The ghost is real. They set up their first experiment at Hanford in Washington State, but the cosmic ray background was too noisy. They could not see clearly enough through all the static, so they moved to the Savannah River plant in South Carolina, where they could get better shielding. They went 12 meters underground. Picture two flat rectangular water tanks, each about the size of a door laid on its side, stacked between three thicker layers of glowing liquid scintillator. The scintillator is the alarm system, a fluid that produces tiny flashes of light when a gamma ray passes through. Cadmium chloride dissolved in the water acts as the neutron trap. 110 photomultiplier tubes, each the size of a dinner plate, lined the walls, staring inward, waiting for any faint glimmer. And they waited. Months of data collection, patient, tedious, exacting work, looking for a signal that amounted to about 3 events per hour. 3 events per hour out of all the trillions of neutrinos pouring through that detector every second. Only 3 per hour bothered to interact. That gives you some idea of the odds. But they found it, the signal was there, the pattern was right. 2 gamma rays, then a delay, then a third, and when they shut the reactor down, the signal dropped. When they turned it back on, the signal came back. It was not cosmic rays, it was not noise, it was the neutrino. On June 14, 1956, Reines and Cowan sent a telegram to Wolfgang Pauli. By then, Pauli was an old man. He had waited 26 years for someone to prove his desperate remedy was real. His response was short. He said everything comes to him who knows how to wait. Pauli died 2 years later. He had lived just long enough to see his ghost become real. And look at what a strange triumph this was. The physicists did not see the neutrino. They never would. Nobody has ever seen a neutrino, and nobody ever will, because it does not interact with light. What they saw was the wreckage left behind on the extraordinarily rare occasions when a neutrino decided to collide with something. It was like solving a murder without ever finding the murderer. All you have are the marks on the floor, the broken glass, the trajectory of the bullet. You reconstruct what happened. You prove the culprit exists, but you never look them in the eye. Frederick Reines eventually received the Nobel Prize for this work in 1995. Cowan did not share it. He had died in 1974, and Nobel Prizes are not awarded to the dead. That is one of the tragedies of this story. 2 men hunted a ghost together, and only one lived long enough to receive the medal. Now you might think the story ends there. The particle is found. Case closed. But this is where the detective work gets really interesting, because catching the neutrino was just the beginning. Once you know the ghost is real, you start asking what else is it doing? And the answer to that question opened a mystery that would last 3 more decades. See, the sun is a nuclear furnace. At its core, hydrogen atoms are being crushed together under tremendous pressure and temperature, fusing into helium. This is the process that makes the sun shine. And every single one of those fusion reactions produces neutrinos. Not a few, not occasionally, every single time. The sun produces an ungodly number of these things. The flux of neutrinos arriving at Earth from the sun is about 65 billion per square centimeter per second. Hold up your thumbnail right now. 65 billion neutrinos are going through that thumbnail every second. From the sun, straight through the atmosphere, straight through your nail, straight through the floor, straight through the entire Earth, and out the other side. And at night, the same thing. They come up through the ground, through your bed, through you, and keep going. The Earth is transparent to them. So in the early 1960s, a chemist named Ray Davis had an idea. He figured, if the sun is making that many neutrinos, and if we know the fusion reactions well enough to predict how many there should be, then we ought to be able to detect some of them. And by counting them, we could actually look inside the sun. We could confirm that fusion is what makes the sun shine. The neutrinos are the only thing that comes straight out of the core. Light does not. A photon produced at the center of the sun bounces around for hundreds of thousands of years before it reaches the surface. But a neutrino leaves the core and reaches Earth in about 8 minutes. Neutrinos are the only direct messengers from the sun's heart. Davis and a theorist named John Pauli worked together on this. Pauli calculated how many neutrinos the sun should produce based on our best model of how the sun works. Davis designed a detector to catch them. Here is what Davis built. Deep in the Homestake gold mine in Lead, South Dakota, nearly a mile underground, almost 1,500 meters below the surface, he installed a tank. Getting there was an experience in itself. You rode down in the mine hoist, a metal cage dropping through thousands of feet of rock, the air getting warmer and damper the deeper you went. At the bottom you walked through a tunnel into an enormous excavated chamber, 30 feet wide, 60 feet long, with a ceiling 32 feet high, all carved out of rock. And sitting in that chamber was a tank the size of a large swimming pool. This tank held 100,000 gallons of perchloroethylene. That is dry cleaning fluid, the same stuff your local cleaner uses to get stains out of your suit. 100,000 gallons of it sitting in the dark, a mile underground, waiting. Why so deep? Because you have to hide from cosmic rays. Cosmic rays slam into the atmosphere constantly and produce all sorts of secondary particles. If you put your detector on the surface, the cosmic rays would create a blizzard of false signals. You would never see the faint whisper of a neutrino through all that noise. But a mile of rock acts like a filter. It stops almost everything except neutrinos. So Davis went underground, into the deepest accessible laboratory on the continent, to create silence. A place so quiet that only a neutrino could reach it. The idea was based on an old suggestion by Bruno Pontecorvo. When a neutrino from the sun hits a chlorine atom, specifically the isotope chlorine-37, it can very rarely convert that chlorine atom into radioactive argon-37. The argon has a half-life of about 35 days, so every few weeks Davis would bubble helium gas through the tank to extract whatever argon atoms had accumulated. Then he would count them. Think about this for a moment. 100,000 gallons of fluid, trillions of neutrinos pouring through it every second. And the prediction was that he would find maybe 15 to 20 argon atoms per month. Not per day, per month. He was looking for a few dozen atoms out of roughly 10 to the 30th chlorine atoms in the tank. That is like searching for a specific grain of sand scattered somewhere across an entire continent. And what Davis found was even worse than expected. He found argon atoms, yes, so the sun was indeed sending neutrinos. But the number was wrong. It was not 15 or 20 per month, it was more like 5 or 6. Roughly 1/3 of what Pauli's calculations predicted. 2/3 of the sun's neutrinos were missing. This became known as the solar neutrino problem, and it drove physicists absolutely crazy for 3 decades. Think about the stakes. If the neutrinos really were missing, then one of two things had to be true. Either we did not understand the sun, our nearest star, the thing that makes life on Earth possible, or we did not understand the neutrino, a particle we had only just barely managed to detect. Either way, something fundamental was wrong, and people argued. They argued for years. There were conferences about it. Careers were built on it. Davis sat in his mind patiently collecting data year after year, and the number never changed. Always about 1/3. He became something of a lonely figure in physics. Many people thought his experiment must have a flaw. They respected him, but they did not believe the result. And Pauli kept refining his solar model, making it more precise, more detailed, cross-checking every nuclear reaction rate and every thermodynamic parameter, and his number never changed much either. The prediction stayed at about 3 times what Davis measured. 2 very stubborn men staring at 2 very stubborn numbers that refused to agree. Let me walk through the possibilities, because this is the kind of reasoning that makes physics honest. Possibility 1. Davis's experiment was wrong. Maybe his detector had some systematic error, some contamination, some way of losing argon atoms. People checked. They checked everything. Davis was meticulous. He ran the experiment from 1967 all the way into the 1990s. He checked and rechecked and rechecked again. The deficit never budged. Possibility 2. Pauli's model of the sun was wrong. Maybe we did not understand the solar interior as well as we thought. Maybe the temperature at the core was slightly lower, or the fusion reactions proceeded differently. But as years went by, and helioseismology, which is basically listening to the sun vibrate and using those vibrations to map its insides, confirmed the solar model with stunning precision, this explanation became harder and harder to swallow. Possibility 3. The neutrinos themselves were doing something we did not expect. This is where a Russian physicist named Bruno Pontecorvo enters the story again. Pontecorvo, way back in 1957, and again with Vladimir Gribov in 1969, had suggested something radical. What if neutrinos could change identity while they traveled? Here is what I mean. We know there are 3 types of neutrino, 3 flavors, physicists call them. There is the electron neutrino, which is the kind produced in beta decay and in the sun's fusion reactions. There is the muon neutrino, associated with a heavier particle called a muon, and there is the tau neutrino, associated with an even heavier particle called a tau. 3 types, 3 flavors. Pontecorvo suggested that a neutrino born as an electron neutrino might not stay an electron neutrino. As it travels through space, it might flip, it might oscillate between flavors, changing from electron to muon to tau and back again. The technical details involve quantum mechanics in a way that I will not torture you with here, but the intuition is not that hard. Picture a spinning top. You paint one face red, one green, one blue. While it is spinning, you cannot say which color it is. It is all 3 at once, flickering through them faster than you can track. If you stop it and look, you will find it on one color. But which color you find depends on when you stop it, which depends on how long it has been spinning, which depends on how far it has traveled. A neutrino works something like that top. When it is born in the sun, it starts as an electron neutrino. But as it flies through 93 million miles of space, it flickers between all 3 flavors. The flicker happens because the 3 types have very slightly different masses, and those tiny mass differences cause the quantum probabilities to drift in and out of phase as the particle moves. By the time it reaches Earth, it might be wearing any costume at all. And if your detector is designed to catch only electron neutrinos, which Davis's was, you would miss the ones that had changed costume along the way. 2/3 of them dressed in disguises your detector cannot see. This was a beautiful idea, but it had a devastating catch. For neutrino oscillation to work, neutrinos must have mass. Not a lot, a tiny, tiny amount, but some. And the standard model of particle physics, which at the time was the ruling theory of how particles behave, said neutrinos were massless, 0 mass. So if oscillation was real, the standard model was incomplete. This made a lot of people nervous. The standard model is not some casual guess. It is the most precisely tested theory in the history of science. Its predictions match experiments to 10 or 12 decimal places. Saying the standard model is incomplete is not a small thing. It means something fundamental is missing from our picture of nature. For a long time, most physicists bet against oscillation. They figured there had to be some other explanation, as there's something wrong with the experiment or the solar model. But one by one, every conventional explanation was tested and eliminated. The problem refused to go away. And lurking behind it was a question even bigger than the missing neutrinos. If oscillation turned out to be real, it would not just solve the solar puzzle. It might explain why the universe contains matter at all, and why anything exists instead of nothing, but I am getting ahead of myself. Let me show you how the answer finally came. Then, at the very end of the 20th century, the evidence started piling up from an unexpected direction. A massive detector in Japan called Super Kamiokande was watching neutrinos produced not by the sun but by cosmic rays hitting the upper atmosphere. These atmospheric neutrinos came in 2 flavors, electron and muon, and the detector could tell them apart. What they found was that muon neutrinos coming from directly overhead arrived at the expected rate, but muon neutrinos coming from below, the ones that had traveled all the way through the Earth from the other side, arrived at a lower rate. The ones that had traveled farther were more likely to have disappeared. They were oscillating, they were changing flavor during the trip. The farther they traveled, the more of them transformed. And that was 1998. It was powerful evidence. But the solar neutrino problem still needed a direct solution. That came from Canada. The Sudbury Neutrino Observatory, called SNO, was built 2 kilometers underground in an active nickel mine in Ontario. It used 1,000 metric tons of heavy water, which is water made with deuterium instead of regular hydrogen. And here is the clever part. SNO could detect not just electron neutrinos, but all 3 flavors. It could count the total number of neutrinos arriving from the sun, regardless of which flavor they happened to be at the moment of arrival. When they tallied up all 3 flavors together, the total matched Bacall's prediction perfectly. The sun was producing exactly the number of neutrinos the model said it should. Not a single one was missing. They were all there. They had just changed clothes. I want you to feel the weight of this moment. 30 years, from 1968 to 2001. For 30 years, two numbers disagreed and nobody could figure out why. Davis was told his experiment was flawed. Pauli was told his solar model was wrong. Both men kept working. Both men kept insisting. And in the end, both were exactly right. The experiment was sound. The theory was sound. The neutrinos were just doing something nobody had the tools to see until Sudbury came along. The electron neutrinos produced in the sun's core were oscillating into muon and tau neutrinos during their 8-minute trip to Earth. Davis's detector in the home-stake mine could only see the electron flavor, so it only caught 1/3. 2/3 had transformed into flavors. His tank of dry cleaning fluid was completely blind to. The sun was not broken. The detector was not broken. Nature had a trick up its sleeve, and it took 3 decades and some of the most extraordinary experiments ever conceived to expose it. Pauli, when he heard the snow results, said he felt like dancing. He and Davis had been right all along, both of them. Davis received the Nobel Prize in 2002 at the age of 88, one of the oldest laureates in history. He died 4 years later. Pauli died in 2005. Neither man lived to see the full flowering of the neutrino physics their stubbornness made possible, but they lived long enough to know they were vindicated. And in science, that is sometimes the most you can hope for. Think about what this means. For 30 years, physicists had a problem they could not solve. Two things that could not both be true seemed to both be true. The experiment said there were too few neutrinos. The theory said there should be more. And the resolution was not that either side was wrong. The resolution was that the neutrinos themselves were more complicated than anyone realized. They had a hidden trick. They could shapeshift, and that shapeshifting required something the standard model explicitly denied them. Mass. This is one of those moments in physics where nature humbles you. We built the most successful theory in history, and then a particle lighter than almost anything else in the universe walked through the wall we put up and said, "Your theory is not finished. There is more to learn." So what do we actually know about the neutrino's mass? Surprisingly little. We know it is not zero. We know it is extraordinarily small. The heaviest neutrino has a mass no more than about 1 electron volt, which in regular units is something like 1.8 times 10 to the minus 36 kilograms. For reference, an electron, which is already a tiny thing, is about 500,000 times heavier. The neutrino is absurdly, almost offensively light, and yet that tiny mass has enormous consequences. Because neutrinos are not just coming from the sun, they are everywhere. About 1 second after the Big Bang, when the universe was still a screaming hot soup of particles and radiation, neutrinos decoupled. That means they stopped interacting with everything else. The universe was so hot and so dense that even neutrinos, shy as they are, had been colliding with other particles constantly. But as the universe expanded and cooled, it crossed a threshold. The neutrinos stopped bumping into things and started flying free, and they have been flying free ever since. Those relic neutrinos fill the universe today. There are about 330 of them in every cubic centimeter of space. Cup your hand right now. In that tiny volume of air between your fingers, there are thousands of particles left over from the first second after the Big Bang. They have cooled down over nearly 14 billion years to a temperature of about 2 degrees above absolute zero, which means they are barely crawling by particle physics standards. They are the oldest free particles in the universe, older than the cosmic microwave background radiation, which decoupled 380,000 years after the Big Bang. The neutrinos decoupled first. They are relics from a time when the universe was 1 second old, and because there are so many of them and because they have mass, even that absurdly small mass, their combined weight is staggering. They probably outweigh all the visible stars in the universe put together. The lightest particle we know may contribute more to the total mass of the cosmos than everything you can see on a clear night. The universe is, in a sense, a neutrino ocean with occasional clumps of visible matter floating in it. We have never directly detected one of these relic neutrinos. They are too cold, too low in energy for any current detector to see, but we know they are there because their gravitational influence shows up in the large-scale structure of the universe, in the way galaxies cluster and the way the cosmic microwave background is patterned. Their fingerprints are everywhere, even if we cannot catch them red-handed. Let me bring this back to you, sitting there right now. Trillions upon trillions of neutrinos are streaming through your body at this moment. They are coming from the sun. They are coming from cosmic rays hitting the atmosphere. Some are left over from the Big Bang itself, relics nearly 14 billion years old, cooled to almost nothing, drifting through the universe at close to the speed of light. A few are coming from nuclear reactors hundreds of miles away. A few are being produced by the radioactive potassium in your own bones. Your body is producing neutrinos. You are a neutrino source, and you did not even know it. And every last one of those particles passes through you as if you were not there. Every second, for your entire life. Not one of them will ever touch you in a way you can feel. The chance that a single neutrino will interact with an atom in your body over your entire lifetime is almost zero. Not quite zero. There is a tiny vanishing probability. But for all practical purposes, you are transparent to the most abundant, massive particle in the universe, and it is transparent to you. I find this staggering. Not because the numbers are big, although they are, but because of what it says about matter. We think of ourselves as solid. You knock on a table, it feels hard. You push against a wall, it pushes back. But that hardness is an illusion of the electromagnetic force. Your hand does not actually touch the table. The electrons in your skin repel the electrons in the wood, and the repulsion feels like contact. Everything you have ever touched, you have never really touched at all. The neutrino does not even get that far. It does not experience the electromagnetic force. It has no charge. The only forces it feels are gravity, which is absurdly weak at the particle scale, and the weak nuclear force, which despite its name is not that weak but has an incredibly short range. The weak force operates only at distances smaller than the nucleus of an atom. A neutrino has to come within that tiny range of a quark inside a proton or neutron to have any chance of interacting, and the probability of that happening is almost laughably small, so the neutrino flies through the spaces between atoms as if those atoms were not there, and the spaces between atoms are enormous. If you could blow up an atom to the size of a football stadium, the nucleus would be a marble at the center. Everything else is empty. You are mostly empty space. The neutrino exploits that emptiness. It does not have to dodge anything because there is almost nothing to dodge. There is a beautiful consequence of this that I want to share. Because neutrinos pass through everything. They carry information that nothing else can carry. A photon, a particle of light, gets absorbed, scattered, bounced around. If an explosion happens at the center of a star, the light from that explosion can take hours to fight its way through the collapsing outer layers. But the neutrinos leave immediately. They fly straight out through all that infalling matter at close to the speed of light. And here is the astonishing part. When a massive star dies, when it has burned through all its fuel, and the core collapses under its own gravity, the vast majority of the energy released does not come out as light. It does not come out as the spectacular explosion you see in photographs. It comes out as neutrinos. About 99% of the gravitational energy released in a core collapse supernova is carried away by neutrinos. The visible explosion, the fireball, the shock wave that tears the star apart, all of that is the remaining 1%. The light show is the sideshow. The real energy is invisible. In roughly 10 seconds, a collapsing star radiates more energy in neutrinos than our sun will produce in light over its entire 10 billion year lifetime. 10 seconds versus 10 billion years. And that torrent of neutrinos streams outward in every direction, passing through the star's own body without slowing down. This actually happened within our ability to detect it once. In 1987, a star exploded in the Large Magellanic Cloud, a small galaxy orbiting our own. It was the closest supernova visible in nearly 400 years. Astronomers named it Supernova 1987A. And the neutrino detectors on Earth, 3 of them in different countries, Japan, the United States, and Russia, all picked up a burst of about 24 neutrinos arriving from the direction of that star, roughly 3 hours before the light of the explosion reached any telescope. Think about what those detectors accomplished. The star was about 170,000 light years away. That means the neutrinos had been traveling through space for 170,000 years before they arrived. The star exploded before human beings had developed agriculture, before we had written language, before we had done anything at all that you might call civilization. And those neutrinos flew through intergalactic space for all that time, arrived at Earth in February of 1987, and 24 of them, out of the billions upon billions that passed through each detector, happened to interact with the water inside those tanks. 24 faint flashes of light, captured in the darkness underground. Those 24 particles confirmed the entire theoretical picture of how massive stars collapse. They told us that the theory of stellar death, worked out on blackboards and in notebooks over decades, was right, and they arrived ahead of the visible light, like advanced scouts from a catastrophe, carrying news of a death that the telescopes would not see for 3 more hours. 24 neutrinos, from a dying star, 170,000 light-years away. That is all it took. Physics sometimes accomplishes world-changing science with almost nothing. Where does all of this leave us? What do we still not know? We do not know the absolute masses of the 3 neutrino types. We know the differences between the masses squared because that is what the oscillation experiments measure. But we do not know the overall scale. Are they 1/10 of an electron volt? 100th? We are working on it. We do not know whether the neutrino is its own antiparticle. Most particles have a distinct antimatter partner. The electron has the positron. The quark has the antiquark. But in 1937, an Italian physicist named Ettore Majorana proposed that the neutrino might be special. He suggested it might be its own antiparticle, a particle in its own mirror image, all in one, a Majorana particle, they call it. Majorana himself is one of the great mysteries of 20th century physics. Shortly after publishing this idea, he vanished, boarded a ship in Naples in 1938, and was never seen again. Nobody knows what happened to him. So the man who proposed the most mysterious property of the most ghostly particle disappeared like a ghost himself. Whether neutrinos are Majorana particles or Dirac particles, meaning they have distinct antimatter partners, remains one of the deepest open questions in particle physics. The way to test it is to look for something called neutrinoless double beta decay. In normal double beta decay, a nucleus emits 2 electrons and 2 antineutrinos. But if the neutrino is its own antiparticle, then occasionally the 2 neutrinos could annihilate each other inside the nucleus before they escape, and you would see 2 electrons come out with no neutrinos at all. Finding that process would prove Majorana was right. Experiments around the world are looking for it now, with detectors made of germanium, tellurium, xenon, and other exotic materials buried deep underground to shield them from cosmic ray noise. So far, nobody has seen it, but the search continues. If neutrinos are Majorana particles, it would explain why their masses are so absurdly small, through something called the seesaw mechanism. And it might also explain the deepest puzzle in cosmology. Why does the universe contain matter at all? The Big Bang should have produced equal amounts of matter and antimatter. They should have annihilated each other completely, leaving nothing but radiation. No atoms, no stars, no planets, no you. But something tipped the balance, very slightly in favor of matter. A tiny asymmetry, roughly 1 extra matter particle for every billion matter-antimatter pairs. And that tiny surplus is everything you see. The neutrino, if it is a matter particle, might be the key to explaining that asymmetry through a process called leptogenesis. The ghost particle might be the reason the universe is not empty. We do not know the ordering of the neutrino masses. There are 3 types, and we know the differences, but we do not know which is heaviest. Is it the one associated with the tau, which would seem natural? Or is the ordering inverted, with the electron-associated neutrino being the heaviest? This question, called the mass hierarchy, is a subject of intense experimental effort right now, and we do not fully understand why the neutrino mass is so small in the first place. In the standard model, particles get mass through interaction with the Higgs field, but the neutrino mass is so much smaller than anything else by factors of millions and billions that many physicists suspect a completely different mechanism is at work, something beyond the standard model, something we have not figured out yet. There is one more thing worth mentioning because it teaches a good lesson about how science works. In 2011, an experiment in Italy called Opera reported that they had measured neutrinos traveling faster than the speed of light. Faster than light. If that had been true, it would have overturned Einstein's special relativity, the foundation of modern physics. The headlines were enormous. People were excited, confused, skeptical. Physicists dropped what they were doing and started checking the numbers. It turned out to be a loose fiber optic cable. A faulty connection in the timing system introduced a tiny error, about 60 billionths of a second, which made the neutrinos appear to arrive early. Once the cable was fixed, the neutrinos arrived exactly when Einstein said they should. The universe sighed with relief and went back to normal. But I love that story because it shows you 2 things. First, the neutrino is so strange that when someone said it might break the speed of light, people did not immediately laugh. They took it seriously enough to check. Second, science corrected itself. The error was found, published, and the result was retracted. That is how it is supposed to work. You do not hide from mistakes. You chase them down and fix them. So the neutrino, this particle that Pauli called his sin, this ghost that cannot be seen, touched, or stopped, turns out to be one of the most important particles in all of physics. It was the first sign that the standard model was incomplete. It may hold the key to understanding why matter exists at all. It carries messages from the hearts of stars and from the first moments after the Big Bang. It outnumbers every other massive particle in the universe. And an incomprehensible flood of them is sliding through you right now, as silently as thought. I started by saying that something was stolen. Energy was missing from beta decay. That was the crime. And Pauli, desperate to save the law, invented a suspect no one could find. It took 26 years to prove the suspect was real. It took another 30 years to discover the suspect had been wearing disguises. And we are still, to this day, figuring out who this suspect really is. That is the detective story. And the case is not closed. It may be the longest-running open case in all of physics. We know the neutrino exists, we know it has mass, we know it changes flavor. But we do not know everything. We have not seen the bottom of this thing yet. And that excites me more than I can tell you, because the most interesting thing about the neutrino is not what we know, it is the size of what we do not. So here is what I want you to consider. Right now, this second, 100 trillion ghosts are passing through you. They have been doing it since the moment you were born. They were doing it before you were born. They have been streaming through this spot on the Earth for 4.5 billion years, since the sun first ignited. And not a single one of them knows you are here. But you know they are there. That is the remarkable thing. You are a bag of atoms sitting on a rock. And somehow, through sheer stubbornness and cleverness, you figured out that invisible particles from the heart of a star are flying through your body at close to the speed of light. And you figured out how to count them. And you figured out they were changing shape in transit. And that discovery cracked open the standard model of physics. If that is not a reason to feel good about being a human being, I do not know what is. Tell me this. If you could detect neutrinos with your bare hands, if you could feel every single one that passes through you, what do you think that sensation would be like? Think about it. 100 trillion per second. I would love to know your answer.